is Dr. Xi from National Research Council. I introduced him as a member of Waterloo. Of course, Dr. Xi actually received his PhD from Western University only because his supervisor moved to Waterloo, and that confused me. And although Dr. Xi moved at once to NRC, and that was correct, as I mentioned. So Dr. Xi is going to talk about time series approaches to compare the COVID-19 mortality data in the province of Ontario. So Dr. Xi.
Thank you, Jianhong. Can you hear me? Is everything?
Yeah, I can hear you, yeah.
Perfect. Let me share my screen. Share. Does this look good?
Yes.
Okay.
It's not full screen though.
Yeah, I know. I could, let me see, slideshow. Try from beginning. How about
Great.
this?
Thank you.
Perfect. So, hello everyone. It is glad to have everyone here today celebrating the launch of this book. And it has been just like yesterday when we were doing this at the first place with Fields. And our team was Charmaine, who was my supervisor. We had George, a postdoc, and Elizabeth, another postdoc in our lab. They were very helpful. Elizabeth is here today with us. She's in the chat. You may find her over there. And then it is me who is now working for the National Research Council of Canada. It was an amazing experience to wrap up this little project as the end of my thesis. And let's go over about what we have been doing for the past 2 years. Starting with the motivation. So what we are looking at are the daily number of hospitalizations, as well as the daily number of new deaths in Ontario from COVID-19. So many people have been looking into this, and we took a quite novel approach or novel perspective by trying to understand if there is any long-run relationship between the two outcomes. This kind of concept has been studied in many fields that are related to statistics. Here, people develop what we call stochastic methods, as Michael talked about before, like the SIR model. You can introduce it, modify it to introduce randomness into the model. Or we can take another approach, just look at the data themselves and then try to see if there's any patterns or features that's driven by the data themselves. Such approach is usually called data-driven approach. And from data-driven approach, one of the methods is called time series models. This model, or these models, has been used extensively in other areas such as engineering, finance, and as well as epidemiology or biostatistics. So therefore, we decided that, okay, let's take this approach and then look at what happened in the wave 1 of the pandemic. That was what's happening in the book. And today, we are talking about what happened after that. So it's like season 2 of the episode. That covers the 3 waves, the first 3 waves of the pandemic in Ontario. And one of the tricky things before we jump into the details is talking about the length of stay in the hospital. Because as you can see that here, we are talking about 2 different quantities. One is the number of hospitalization, one is the deaths. There's this lag effect. So if you want to compare them, there has been extensive studies talking about after how many days you will see the effect of hospitalization reflected on the number of deaths. So a very naive assumption I'm making here is that we're assuming the median length of this quantity is 8 days. And there's definitely limitations associated with that. But for now, let's just take it as a given and look at the data. This is the data for the 3 waves. The figure contains a blue curve, which represents the number of hospitalizations, and a red curve represents the number of new daily deaths. Notice that these are not cumulative. These are just the daily number of new numbers that you observed on every day. So you can clearly see that there's this zigzag seasonality issue going on throughout the 3 waves. As well as, for each wave, there's only a certain specific time periods where the variation becomes of interest. So the bolded curves, the bolded parts of the curves, are actually the 3 parts of data sets that we are trying to develop the model with. Now, talking about the model we are looking at, or we have been looking at, what we were looking at in the very beginning was called a autoregressive model. That means the number of cases you see today depends on the number of cases yesterday. That makes intuitive sense. And that approach has been generalized by the domain into something called autoregressive integrated moving average model. So shorten it up, it's called a RIMA model. You probably have ever heard about it. Now, let me give you the general concept of it, and then I will talk about an easy representation of a simple representation of a special case we are looking at. The general concept is sort of like a regression type of model, linear regression type of model. For observations, we index them with t equals 1 to n. On the left-hand side, here we are having the number of, either the hospitalization or the number of deaths. It doesn't matter, you choose one. The number of such patients on day t. And on the right-hand side, you have an intercept term representing the baseline effect of the numbers, and then plus some kind of random error. Now, what about those other fancy terms? Starting with the D, this is called a backshift operator. It pretty much means that if you multiply this operator to your YT, you can get YT minus 1, YT minus 2, YT minus 3, which is the number of patients 1 day ago, 2 days ago, and all the way to T days ago, or whatever numbers of days ago. We take this quantity and then scale them or multiply them by this kind of coefficients. These psi's and deltas, they are the coefficients representing the degree of effects that's associated with the observations on the previous days. So you can imagine if this quantity is estimated to be big, then of course the previous days have a huge effect on what you're going to observe today. You do this for not only the observation themselves, and you also have this coefficient for the error terms. And not only that, sometimes your data set is actually not that easy, so you've got to transform it somehow to make it follow certain kind of distribution. And one way to transform in time series model approach is by taking a backshift difference between that. That means in terms of, rather than just looking at the daily numbers, you take a look at the difference between today and yesterday. And you take this difference as your first data point. And then you look at the difference between the next day and today. And then you take that difference as your next data point. By taking this, your data set will may more or less follow a well-known distribution. And the well-known distribution, or the baseline well-known distribution we are assuming here, is simply just a white noise, following a normal distribution with mean 0 and a constant variance sigma square. Now, if we are all lost, then let's take a look at a simple case. A simple case here is the ARIMA 011 that I will be using for this analysis. The second term is a 1. That means on the left-hand side, we are taking indeed the day-to-day difference of the number of observations. And then the third term is a 1. That means we are indeed just finding an error term of today, and as well as another error term which is from yesterday. So imagine if you include error term from 2 days ago, that will be a 0, 1, 2. That's basically the logic behind it. So with that, there is a nice interpretation of this model. If you fit the data to the model, the short-term influence of the past is reflected through this coefficient theta 1 before the error term. And the long-term influence of the past is expressed by this quantity, still in terms of theta 1. And this term, you will see it again, is sometimes termed the autocorrelation function. And our goal is try to fit our data into the model, find the best model, and then get these estimates of the parameters. So to do any fitting, we start with some exploratory analysis. First, as I said, we're going to segment the study into 3 periods. Each period contains exactly 3 months, just for the sake of easy comparison. And that's pretty much also what happened before. And after we fit the model, we will compare we fit multiple models, and then we're going to compare and pick the best model. That model selection criteria we are using here is the Akaki information criteria, the AIC, as well as we'll be looking at some visualizations to see if you can actually tell that this model on the graph is the best. So here is the result. First, looking at the numbers, the AICs. Here again, we are using a RIMA model, and we're gonna have 6 different models for each row. So I mean, for each row, we are having 1 model, so there are 6 candidate models we are looking at the very beginning. And the naming system, as you can see, the nomenclature, it's based on how many parameters you are including for the autoregressive part, for the integration part, and for the moving average part. And of course, you can include, like I said before, you can include the 2 error terms, which is related to the error term happening from the day before yesterday. But just for the sake of beginning, let's take a look at just include 1, what's going to happen. So take that combination and then fit the model. If you wonder what kind of method we were using here, we were just using R packages based on iterative approach in a frequentist approach. But if you ever read the book from before, if we would like, this model can be definitely extended by including other random variables in the model. And then in that case, I was using a Bayesian MCMC approach, the same as Michael was using in the beginning. And here, coming back to the result, the fits tells us that it seems that if you take the day-to-day difference by 1 day and then just include 1 extra error term at the end, that model termed ARIMA 011 seems to give the lowest AIC for both the hospitalization and for the death across all 3 waves. This is a little bit different from what we did before, because if you remember, in the very beginning in the book, we only did autoregressive. We didn't consider this more general case. So it is actually a good update to our study result. And the other question that I left before was, are we able to, or do we need to include more error terms? Or do we need to include more observations, like observations from 2 days ago, 3 days ago? And that can be visually validated from these exploratory plots. If you ever remember the autocorrelation function that I was talking about before, you can include as many numbers of terms in your model, and then check if that quantity is significantly different from 0. And here, this kind of plot does the work. They include all the way to 20 terms, and then you can see that it is only the first, the quantity are at including just one lag is significant. It is an indication that yes, it is enough to include just one error term, or in other words, lagged by 1 day is enough. And this is for wave 1, and the similar feature was demonstrated for wave 2, wave 3, and everyone. So just not showing for the sake of time. Or another thing, if we are really into this fashion, there's a thing called partial autocorrelation function. That is basically another kind of correlation function. It's more complicated, and it tells you whether other terms that you can include in the model. Here, as you can see, as long as these two plots are having this geometric decay, then that also represents our model here by including one term for the moving average. That should be good enough. And the other thing that I was trying to talk about is these two plots on the left, especially the one on the top. So this is recall for wave 1 only. So I took that little chunk, take the two curves, and then here I plot their day-to-day difference. So rather than plotting the raw data, I subtract today from yesterday, and then plot this data. You can see that clearly the data becomes more what we call stationary. So which means this kind of transformation will ensure us to have a better model. So that was everything about model fitting. Now here comes the result. The estimates are here in colors, and the standard errors associated with them in the brackets. Standard errors are relatively small, so the estimates are quite precise. And what we can see is that here I have estimates for hospitalizations and deaths for wave 1 to 3. And then this gives you that the short-term influence of the past is actually decreasing over the 3 waves. It's an important feature that we observed after we have data for 3 waves. And on the other hand, for deaths, the short-term influence of the past actually increases over the waves. So these are all new findings that we have observed, and the long-term influence of the past remains fairly constant. So if you want to extend this study a little bit more, you can compare the relationship between these two. We're not going to go through the details, but just giving the results saying that the two time series processes, they are related in this long-term relationship, and that can be tested using this co-integration approach. And our analysis at the end saying that yes, for all 3 waves, the number of hospitalizations and the number of deaths, they are related in this long-term stochastic approach. As this relationship is especially strong for the 3rd wave. That is basically what we have found in the past year. Now, what's going to happen next? The lab is still ongoing. They are still doing research on this topic. There are new students and new postdocs getting in, and they are looking at studying the viral load in the wastewater. That can be used as another indication to find its relationship with number of hospitalizations. And this whole general framework can be utilized in developing a risk framework for emergency response to any kind of natural disasters, which is kind of related to my work there at NRC. That's pretty much everything I'd like to share today. Thank you for the time. Thank you for the chair. I hope you enjoyed the rest.
Well, thank you very much, Dr. Shi. So we collectively saved 2 more minutes for I